All right, let's try this next one. So here, same thing. This time it's a quadratic function. We want to find the derivative. And so we want to find f prime of x. And we know that the formula for that is the limit as h approaches 0 of f of x plus h minus f of x all over h, right? So we're going to take f of x plus h. So what that's going to do is we're going to plug in we're going to plug in x plus h there and x plus h there. So it's going to be a little bit of work here. So it's going to be x plus h, or let me do it on the side over here. So x plus h, f of x plus h is going to be x plus h squared, quantity squared, minus 2 times x plus h, right? So the shortcut works here, so that's going to be x squared plus 2xh plus h squared. And then here when I distribute, I'm going to get negative 2x minus 2h. So we can combine like terms. So yeah, I don't see any like terms there. Yep, I don't think we have any. So we're just going to bring that over, put that in place of this. And so it's going to be x squared plus 2xh plus h squared minus 2x minus 2h, and then minus f of x. F of x is just this, right? So it's just going to be minus, and then we're just going to put in x squared minus 2x, right? Which is what this is. Okay, then it's going to be all over h, and the limit as h approaches 0. So what's going to happen, and we've seen this before, but basically our x squareds are going to cancel out. 2, and I forgot to put parentheses around here. When I subtract this value, I have to subtract that whole value, right? So it's actually negative 2x minus negative 2x, right? So that ends up, those do end up canceling out. And then we have x squared minus x squared. And so those will cancel out. All right, and then let's see, no more like terms. And so I'm going to bring down what I have left. So it's 2x h plus h squared minus 2h all over h. Okay, so good news is they all have an h in common. So we can factor out an h. So it'll be h, the quantity of 2x plus h minus 2 all over h. And then we can cancel out these h's here, right? They go away. And so we end up with the limit of, as h approaches 0, of 2x plus h minus 2. And now we can actually directly evaluate, right? So we can plug in 0 here. So it's going to be 2 times, or 2x plus 0 minus 2. And so it just turns into 2x minus 2. All right, so that's the derivative of f of x. And so that's our final answer. All right, so that's what happens when we do a quadratic. And hopefully you'll start to see some patterns as you've done these. Maybe you've seen them already or noticed them already. But when you have a quadratic, there's some features about this that will kind of replicate. You'll see a pattern. Now let's take a look at this graphically. So we just got this, where we started with this function, right? X squared equals, or f of x equals x squared minus 2x. And we found the derivative, and we found it to be 2x minus 2, right? So our original function was a quadratic, a parabola, right? And our new function is, or our derivative function is a linear function, okay? So we'll talk about why, why this is to some extent a little bit later on. But for right now, in terms of like understanding the the derivative versus the original function is, remember that like the original function, the values of it don't matter by themselves, but the slope, right? The slope along the line matters. And so notice how here we have a negative slope, right? And so when we have a negative slope, what happens is our derivative is negative, right? Notice how it's below the x-axis, right? So everywhere where the slope is negative here, the derivative is below the x-axis, okay? And then when the graph turns to have a positive slope, that's when the derivative function is above the x-axis, right? It's positive. And of course, remember the peaks and valleys are where our derivatives are 0, or where the slope of the tangent line is 0. And so notice how at that point, at that peak, our derivative crosses through the x-axis, and it's essentially equal to 0, right? Okay. All right, and so that's that kind of gives you an idea of the graphical representation of a function and its derivative. And so so we went from a quadratic to a linear. So think about that, and that'll be something once again that we'll talk about later on. And then I forgot to show you the graph on the first function that we did. We had the function which was square root of x. We took the derivative and we got 1 over 2 root x, right? And so so this is the original function here, f of x, and then we have our derivative function here, right, which is f prime of x, 1 over 2 root x. And so we can see that what's happening with the derivative is the slope is positive, right? And it's super steep right here in the positive direction, and then it kind of levels out. So it's still positive, the slope is still positive, still going up and to the right, but it's getting smaller and smaller, right? It's kind of leveling out, flattening out, going towards 0. Okay, and so the slope is going towards 0, right? The function keeps increasing forever, but what we can see here is this graph is high right here, right, where it's steeper. Okay, so the derivative has high values there, but the slope of this line is decreasing, so that means the derivative is decreasing, right? And so then it kind of levels out, and it's not decreasing as fast, but it's still decreasing. All right. So you can see the relationship between the slope of the original function and the values of our derivative, right? Because our values are those slopes at each instantaneous point. And so if I wanted to find the slope of the tangent line at this point where x equals 2, then I could just plug in 2 into here, and that would give me the answer, right? And so I can find f primed at 2, and that would give me the slope of the tangent line at this point. Okay. All right.